Hello Internet, welcome back to the Dining Philosophers problem. Today we are going to be solving this problem. We demonstrated the issue we were having in the last video, and now it's time to solve it. We're actually I think we have time to do both of the solutions I have in mind. So our issue, if you do not remember, is we have 5 people eating at a table, and there are 5 chopsticks spread around the table. One shared between 2 people sitting around the table. So philosopher 0 and philosopher 1 share a fork in between, or a chopstick in between them, and it goes all the way around the table just like that. So what happens is they can't eat unless they pick up both chopsticks, and what's happening is we have 5 philosophers. They're each picking up all of their chopsticks to the left, and then not being able to complete what they need to do. And so eventually they all have one, and nobody else can pick up the second to actually finish eating, but they're not releasing their chopsticks either. And that's causing this issue. So in order to fix this deadlock, what we need to do 2 things. One of the solutions is to introduce a waiter that says, yes, you can acquire chopsticks, or no, you can't. The other is going to be what we're going to start with, and that's going to be introducing some oddball. And the way we're going to do that is we're actually going to prioritize the chopsticks that get picked up. And the way we're going to do that is we're going to have every philosopher pick up the highest indexed chopstick first. And the reason this solves it is because there is a little bit of a wraparound. So you see we have this get chopsticks right here. What this is doing is it's getting a chopstick index, mod the number of philosophers. And so what happens is that philosopher number 4, they are going to get an index of 4 here, and then this one is going to be index 0. And so that's going to be a different pattern. Instead of picking up their left chopstick, for example, first, they're going to pick up their right one first. And so what that's going to do is if that right one is already taken, they won't pick up the left one, and so the person to their left can pick up their right chopstick, because that's just how it works. And so that way we never get this deadlock situation, because nobody can pick up the same chopstick. Or there's always that one oddball that's picking up the opposite direction, and so it avoids anything bad happening. The issue with this is it isn't perfectly concurrent. Neither of the solutions we're doing are actually going to be perfectly concurrent, and that's because you could have all but that one special guy locked until he releases his stuff, and we don't. That's not necessarily a good thing, but it's the solution we're going to go with. So theoretically, we probably could introduce additional odd people, but we're just going to do one because it's probably the easiest. And so the way we're going to do that is we're going to actually do a little bit of link. So we have these 2 chopstick indices. We're going to call them chopstick 1 and chopstick 2. And we can just do something like this. And now this code probably isn't going to be super clean, because we're just kind of getting our ideas out there. But what this is going to do is I can actually remove this now. That's not needed at all. And I'm just going to leave this here with an empty index. And then what we want is we want a new list of our indexes. And it's going to have chopstick 1 and chopstick 2 inside of it. And then what we're going to do is on that, we're going to order by I. And that's pretty much all we have to do there. So this is a link statement. I think I did that wrong. Can't use I because it's up there. Sorry. So we're going to call it the index. Like so. And so this is a link statement. I was kind of going over this a little bit, but it's going to order a list. In this case, it's ordering our 2 chopsticks by their index. And so that's going to get us that order. And then we should be able to call something that can do what we need with this. I forget what it is. Let's just do it the easy way. So we have an ordered list now of our chopsticks by their index. If we send that out to a list, like so, and then save it as the chopsticks list, then what we can do is just iterate over these. So for each, can we do that? Yeah, we have, because we have indexes, sorry. So for each chopstick index in the chopsticks list, we want to plug that in. And so we're still going to wait on both of these chopsticks, but we have that one special guy now because he's going to be ordered in the reverse way. And that should be all we need to do, actually. So this is going to just order our indices, and then we're just going to do exactly what we had. So we added 6 lines of code, and well, if you don't count this one, 5 lines of code. And actually, if you don't count those, even less. But point is, it's not that much work, but this should actually work, I think. Yeah, so you can see we finished eating. I'm just going to run that a few more times because we did have some issues where it was actually going through and not being done. This is the best way I know to just be sure there were no logic errors. This logic should work. I've done this before. And so this style of solving the problem is fine. It's actually the original solution proposed by Dijkstra. I think I'm pronouncing his name right. He's the guy who came up with this problem way back in like the dark ages of computer science, but he was the guy who initially proposed this problem, and this was his proposed solution. So that's what we have. What I'm going to do now is hold undo a bunch. Actually, no, that's a really bad idea because somebody's going to want this code. We're going to do that and then copy it and paste it somewhere. This isn't the best solution to this problem, but it's a solution to this problem. The best solution would be source control, but it isn't under source control yet. It will be, which is a totally different issue. I'm just not there yet. But then we can undo everything we did here and get back to here. And the only other thing we have to do is I had fixed a spelling mistake because I do not know how to spell philosopher. And this is where we were initially. So I should be able to start this again and we'll get deadlock again. So philosopher 0 is just attempting to get food and he can't. Right. So now the best way to do this is the waiter method. And so how we're going to do that is we're going to create a static semaphore slim. That is going to be our waiter. And so what this is going to do is it is going to wait. Let me think about this solution a little bit. I have not, so like most of my videos, I have not considered the actual solution. The last one was easy because I kind of worked that out as I was thinking about it. This one I haven't thought about as hard. And so what I think we want is we actually, so there's a few fun things going on here. And the reason it's fun is because you can have, with this solution, we can still have multiple people eating at the same time. We don't have to have one person eating and then pass it off to the next person and so on. 2 people completely across the table can eat by themselves. That's fine. There's nothing, we shouldn't stop that. So we need to account for that in our solution, which I do not know how it's going to work yet. So we have this for loop. The one thing we do want to make sure is everybody eats 100 times. What we don't want is we don't want to do a test and then skip out of this. So I think we can do a waiter release down here. And so this becomes a protected block. So you can't get in here without having permission from the waiter. Now this should work. I can run this and it'll work. The issue is we just turned our, whoops. Nope, that doesn't work. I should have actually seen what the error was. Oh, we didn't initialize our waiter. There we go. So if I start this, it'll work. The issue is we just converted our parallel program into a serial program. There was no concurrency there. It didn't exist. We literally just, like, all of these other semaphores aren't being used at all because there's just one and they're all acquiring it and it's breaking everything. So this doesn't work. What we do want is a waiter release up here. And then we want to do some sort of logic in this block here. And we actually want to acquire them as well. So the thing is we can acquire these chopsticks in our semaphore like so, and we can release them out. Does our release need to be synchronized as well? Maybe. I don't think so. We'll find out. I don't think the release needs to be synchronized, and the reason is because this will just evaluate to false. Will it though? Yes. Because worst case, we release something and then this just immediately acquires it. I don't think that's a problem. So we're going to have our philosopher calling the waiter. Attempting to get chopsticks. And there is that. So there they attempt to get their chopsticks. They're inside of their waiter task. So they've asked the waiter for chopsticks. Then the waiter has to say yes or no. And so the way we can do that is we want these indices again. Probably could have saved that, but oops, that's not how you do that. Chopstick 2 and chopstick 1. So we have 2 chopsticks. They're there. We can put those back where they came from, like that. And now what we need is we need to actually test if our chopsticks, chopstick 1 dot what is it? Current count. I believe current count is greater than or equal to 1. Greater than 0. That'll work. And so how semaphores work is they have a counter. You can see there's this 1 up here. And so that count is the number of available things in it. It's just a counter that goes up and down, but it goes up and down atomically, which means nothing else can interrupt it. So when we're incrementing this count or decrementing this count, nothing else can get in the way of that. So what that allows us to do is say the way a semaphore really works is it just has a count. In this case, it's 1, which means one thing can get in. When we wait for something, that is going to decrement that count, and then it's going to let whatever it is pass. If it's below its threshold, or if it's 0 or below, that semaphore is already blocked. Nothing can get in. And so what happens is we hit this, it's 0, we stop. All this is asking is if our current count is greater than 0, then we can get in. Chopsticks. And I'm starting to think I don't like this solution because I have a feeling it seems like it's introducing a lot more issues. It's more code, and I don't like writing code is fun, but at the same time, the more code you write, that's more code you have to keep up to date in the future when you have an actual application using logic like this, and that's less fun. So we have this check is going to see if both of our chopsticks are available. And since the only time the count can be decremented, so the only time it would fall into this condition and make this false is inside of this lock, this should be safe. If we move these outside of this waiter block in here, then this becomes a problem because it's possible for somebody else to acquire it while we're doing it. Since this is this whole block is going to execute by itself, we're ensuring that nothing else is going to acquire anything while we're in here. So in here, if this happens, then we want to acquire stuff. Otherwise, we are going to want to log out a message. Failed to acquire chopsticks. Sure. And then, if this was successful, they'll fall out. Otherwise, we'll just continue for now. So this is going to break things. So for a really cheap hack, don't do this. This is bad. But what we can do is, since we're incrementing our count every time, we can actually just decrement it. That's a really bad idea, and I'm going to regret doing that. But it will get us to the point where I can actually run this and see what happens. So we can start this. Oh, shoot. I'm expecting not this. Something's going wrong. We weren't seeing any other output. We were seeing calling the waiter and attempting to get chopsticks. And then it looks like they're getting deadlocked in the calling the waiter bit. So calling the waiter, attempting to get chopsticks, that's good. One of the things to note is these consoles are buffered, which means things can be a bit out of order because we should never see a calling the waiter followed by another one because there's always another console message after it. Just because we're seeing that does not necessarily mean things are broken. In this case, they are broken, but that is irrelevant or less less relevant. What did I do? Created a lot of deadlock by doing something silly. If both the current counts greater than 0, I'm guessing this is the issue. That seems like it would be the issue. One thing I'm noticing, just so we have some consistency, we can swap those out. Huh, okay. Don't know what's going on. I'm thinking I'm screwing something up. Well, I know I'm screwing something up, but I don't know what it is. The conditional has to be wrong. And I think it's the problem because I'm using semaphores of semaphores of semaphores of semaphores, which is probably bad. So that's not a good way to do this either. Just to amuse myself, I'm going to actually log out those numbers because I'm kind of curious now. So we can do 1 is going to be our chopsticks, chopstick 1 dot current count, and whoa, it's getting all sorts of fun formatting on me. There we go. And then the next one, 2, is going to be chopsticks, chopstick 2, and we'll log the current count of that as well. Really wants to put that on a new line, and I don't know why. Oh, pressed all the wrong buttons there. There we go. So this is just going to log out the 2 chopstick numbers. Going to put the actual indices in brackets so we can distinguish them from the other numbers we're going to be logging. And then let's see what this prints. I'd expect some zeros. And we got that, which is good. So things are actually happening. I'm guessing my assumption was incorrect. These counts are not synchronized, which is a problem. I'm thinking of all of these really bad ways to solve this problem, and I don't want to do that because that's just not a good idea. We'll end up getting into way more trouble if we start implementing all of these really quick and easy solutions. So what's confusing me is we only got 2 prints of this message right here, which does not make that much sense. Now, the reason it doesn't make any sense is because we don't have any locks in here, unless it's oh. Is that the issue? Oops, sorry. That would make sense. So what was happening is we have this block here. This is our really, really sketchy, gross logic here. And so it was logging out, failed to acquire chopsticks. I don't know why we weren't seeing that. But my assumption is we were getting here. And we were just hitting this continue and jumping out, which means we never released our waiter, which means we deadlock everything. And I'm guessing we aren't seeing this because, why do we see it multiple times sometimes? I think it's probably a buffer thing. I'm going to go with the buffer theory. That's my guess. Cool. Okay, this is more like what I was expecting. And so here we can actually kind of see what is happening. I did not log the philosopher number by these, so it's kind of hard to tell what's going on. So let me add that and rerun it quick. There we go. And now if I start this, we'll be able to see exactly what is happening. And you can see we've got some intermingling of stuff. This is going to have, it's not going to be the perfect concurrent solution to this problem. Those are hard. So these are the two we've gone through have been, they're the ones that actually solve this problem the way it was written, which is you cannot allow your philosophers to actually discuss with one another about what they're going to do. The best solution I've seen actually uses sort of a messaging pattern. And so each of them will actually ask, can I grab this to the guy or to the philosopher who is beside them, and see if it's okay if they grab it. But that requires them to actually communicate, and they're too busy for that. They're talking about the meaning of life or whatever. They clearly have not read the proper books. The answer is obviously 42. But here, what we're getting is we're getting a waiter who is going to only allow them to acquire chopsticks if both of them are available. And we see that happening here. And I think that's what we want. So I would recommend Dijkstra's solution. That seems to be, not only is it easier to implement, but it also, there's less control. And what I mean when I say that is when you have all of these semaphores and so forth, managing them is really difficult. You saw I was kind of screwing around with them. Like I had this happen. That's bad. And if somebody else has to come in here and look at this and be like, what was he doing? They aren't going to have a bit of clue what I was doing. So I don't recommend anything that requires you to do something like that. And granted, this solution does not require you to do something like this. This is just implementing it to, what we're trying to do here is I'm not trying to show you the best way to solve these problems. I'm trying to show you what the problems are and a way to solve them. If there's better ways to actually solve these problems, I'm just kind of covering, here's how we get to those problems, and here's how we solve them. And then if you want to go and refactor this down and make it really clean and good and all of that, then go for it. But I'm not going to do that because that, one, it takes a lot of time, and two, everybody's kind of style is different. And this way, I think it kind of makes it a little bit more cross-language, and people can kind of hopefully bring this to, say, Java, for example, or even like C++ or any of those other languages. So if you want to do that, go for it. If there's anything else I missed, or you have questions or anything like that, sorry, I'm losing my voice. But if you have questions or anything you want to ask me, leave a comment and I will do my best to answer those. If there's something else you want to see, or there's just anything really, leave a comment as well and I will check those out. But until next time, see you, Internet.